right? So we are looking into the ELF format, right? And the ELF format essentially has two views. It has a linker view, which we see here, and the executable view, which we will essentially see later. So things like the object files and libraries, which are essentially typically make use of the linker view. So anything with a .o or um, .so, which is a shared object, would essentially um, in for these particular files, the linker view is essentially more important. Okay, so let's look into the details or into the internals of these ELF files. Right, a typical ELF file has several sections and segments. It has a ELF header. It has section header table, and then various sections. Here that we see essentially 4 sections, and you could actually read more about the ELF either from this reference or by essentially seeing the manual for ELF in your Linux machines, right? So if you do man ELF, it gives you details about the ELF format. Okay, so what exactly are these headers? What exactly are these sections, right? So the ELF header is common for both the linker view as well as the executable view, right? It comprises of multiple different items, some of which are essentially highlighted here. So the ELF header has a field known as identification, essentially to identify, which is used as a signature to essentially identify this particular file, right? So your typical ELF file would start with these 3 letters, ELF, ELF, indicating that this is an ELF file, right? Other fields in the ELF header are the type, the machine details, entry, pointer to program header, and so on, right? The type essentially tells you the type of this particular ELF file, whether it's an executable, whether it's an object, whether it's a .o file, which is a relocatable object, whether it's a shared object like a library, or whether it's a core file, right? So this information is essentially encoded in the type present. Okay, the machine details essentially tell you for what processor this particular ELF file is compiled for, right? So one thing to essentially note is that each processor has a different instruction set architecture. So a program that is compiled for RISC-V would not work on ARM, and similarly a program which is compiled for ARM would not essentially work on x86 and vice versa, right? So the machine details essentially tells you whether this particular ELF file is compiled for an Intel platform like an i386, which is a 32-bit Intel platform, or a 64-bit Intel platform, or ARM, MIPS, RISC-V, etc. Right? So this information is essentially encoded. Then you would have a field called entry. So entry in the ELF header tells you where the program should begin execution. So for instance, if my program wants to execute from this function called main, right, then the virtual address of this particular main program or main function should be essentially filled in the entry, right? So when the operating system, how is this essentially going to be used? So when the OS starts to execute this program, it needs to identify what is the first location, or what is the location where it should start the execution from. For that, it needs to know something like where the first function, like the main function, is present, right? So the operating system will look into the ELF header, look into this entry field, identify that this is the what is the address that has the main function, and then set the program counter in such a way that the main function executes, right? So other fields which are important in the ELF header is a pointer to the program header and pointer to the section header, right? Now, so recollect that in this figure we said that there is a section header table and various sections, right? So what this means is that or within the ELF header we would have a pointer which is essentially pointing to the section header table. In a similar way, we would essentially have another pointer which points to the program header. So it's not shown in this particular figure, but if there's a program header present in your ELF file, then the entry in your in your ELF header, namely the pointer to program header, would essentially point to the appropriate header, right? Also present is the number of program headers and number of section headers as well, right? So so pointer to program header, as we've said, it is essentially a pointer to an offset within this particular file which has the program header details. Similarly, a pointer to section header is an offset within this ELF file which comprises of the section header table, right? So we'll now see an example of such an ELF header, right? So we'll take our very famous example by now of a main function with which just prints hello world, right? So what we are doing now is compiling it, but notice that we are using the -c option during compilation. So this would essentially generate a file called hello.o, which is of the ELF format, right? Now we can use this utility called ReadELF to essentially look or to provide internal details of this of any ELF file. So here, for instance, if I use ReadELF with -h option and then hello.o, I would essentially be able to print the ELF header for this file hello.o, right? Here is a snapshot from my system. So first of all, what we see over here is that there are various fields, right? Many of the fields are present here, like identification, type, machine details, and so on. There are a few other fields also which are present, which for us as of now is not very important, right? So we start off with the magic, a magic number, which would be a unique signature that would essentially denote that this hello.o file is essentially an ELF file. So when the OS executes, or when let's say ReadELF itself executes, it would look into the file and validate that this particular magic number is essentially correct, which would indicate that this is possibly an ELF file. Okay, so other important things, for example, over here, right, is the aspect of type. Okay, so as we have mentioned, the type could be, say, an executable, a relocatable object, a shared object, and so on. Here, the type is a relocatable file, right? And by relocatable file, it is essentially indicates that it's an object file, and object files are essentially relocatable. The meaning of or why this file is relocatable is that the addresses are not fixed. What it means is that within the if this file is loaded within a virtual address space, it can be loaded at any virtual address, right? So this gives the flexibility to the OS to essentially and to be able to manage the virtual address space of a process more efficiently. Okay, so a type of relocatable file essentially indicates that it is an object file, could be also a shared file as well, a shared library as well. The other thing that we also looked at is the machine details. So this particular object file is essentially of the form x86 64. That means it is compiled for a 64-bit AMD device. Essentially, it would work with the Intel 64-bit platforms as well. Okay. Now, third, we have the entry point, right? Notice that the entry point is set to 0. So, what does this mean, right? So, ideally, as we've discussed, the entry point should contain the address of the main function or the first function that needs to execute. But here we are looking at an object file, and an object file cannot be executed, right? And therefore, this entry point address is set to 0, right, indicating that this this particular file cannot be executed, and this entry has no meaning for this particular file. Okay, so then you would have the other thing that we want is the start of the program headers and the start of the section headers, right? So these are essentially labeled as pointer to program headers and pointer to section headers. Now, one thing to note is that for an executable, the program headers is what is important, while for an object file or any other relocatable file, it is the section headers which are essentially critical. So here we see that the pointer to section headers or the start of the section headers is at 368 bytes. So this means that at an offset of 368 bytes in this hello.o is where you would find the section headers. Okay, so so what we can also see is that the size of the section headers is 64 bytes, and the number of section headers is essentially 13. Okay, so let's go a little more detail, more further, and try to look at these section headers. Right now, for this particular program, if I use readELF with the minus capital S option and then hello.o, it would essentially read the section headers from the offset of 368 bytes. Right. So recollect that this header, section header, is of size 64 bytes and comprises of 13 bytes. So with this command readelf -s hello.o, we are able to list the various sections present in the section header, right? So what we see is that there are the sections are labeled 0 to 12, 13 sections. There are text sections, relocatable sections, data sections, BSS, read-only data, comment sections. There are various different types of sections, right? And you have the type as well. So the type of this section determines whether these comprise of code, which is essentially program bits, as we see over here, or programming. It essentially has information relevant to the execution of the program, like code or data, or things like that, or read-only data, things like that. So the other type is the no bits, essentially, which indicate that this is just a marker. It essentially occupies no bits. Rela, on the other hand, which is present over here, is a relocatable table. Similarly, you have a symbol table, which lists all the symbols, all the functions, all the global variables that are present within this object file. That would be in this section called symbol table here, as we see here. And programming bits are essentially defined by the program, as we've discussed. It could be the code and data and so on, right? The next field in the section header is the address, right? Now, this column essentially comprises of the virtual address where each of these sections should be loaded, right? So, for example, I have a .text section, which essentially comprises of code, which has to be loaded into my process, into my process when the OS essentially creates the process, right? However, here we see that this region is set to 0. Now, Why is it set to 0? Because for object files, the first, the object files are relocatable, so virtual addresses does not make sense over here. And second, you cannot essentially execute an object file, it needs to be an executable. Therefore, this column does not make sense. Okay, so the fourth column is essentially the offset. So what the offset essentially says is where the section is present within the where the section is present within the ELF file. So going back over here, we see that there is a section header table, and the ELF has a field within the ELF header which points to the section header table, right? Now within the section header table we have 13 entries, and each entry has a pointer to the corresponding section, right? So we have such pointers stored in the section header. Now when I say pointers over here, it doesn't mean the memory pointers that we've used to in C, but essentially these are offsets within the within this particular file. Okay, so what does this mean? So at a offset of 40 bytes from the section header, we have this text section. At an offset of 5f8 bytes, we have this relocatable dot text section, and so on. Okay, this next field, the size, essentially tells you the size of each section. The dot text section has a size of 5c in hexadecimal notation. The dot rela dot text section has a size of 48, and so on. Okay, and the last this column ENT size essentially is applicable for tables, right? If it is a table, then the corresponding entry would tell you the size of that particular table. So for example, we have where is the table, like the symbol table, right? So this is a symbol table, and it has 18 bytes in hexadecimal notation. Okay, and besides this, we have a lot of other flags and other information present about each of these sections, right? So if I think about it, let's take the text.text section, which comprises of, say, the code, and I go back to this, this slide here. So we have one section in the section header table which essentially points to this dot text. Now this section 1 would present at a specific offset 40 bytes, as we've seen, would contain the code for the particular program. Okay, we will now so recollect, we mentioned about the linker view and the executable view, right? So we would now look at the executable view of a ELF file. So when we are looking when we are talking about the executable view, what is important for us is the program header table, right? And the program header table, very similar to the section header table, would comprise of different segments within the program, different segments within the ELF file, and pointers to these different segments are essentially present within the ELF header table, right? So as we see over here, the program header table contains information about each segment. The segment could be text segment, data segment, and things like that. There is one program header for each segment. Okay, so here, for example, we see 4 segments, and therefore within the program header table we have one entry corresponding to each segment, right? The program header entry also contains various other information, just like the section header table, right? And we can actually see this in more details, because this is what is actually useful for us from an executable perspective, right? The program header contains type, which is the type of segment. It has the offset of the corresponding segment within the ELF file. It has the virtual address offset, and it also has the physical address offset, right? So the virtual address offset essentially tells you where the segment needs to be loaded, while the physical address offset specifies what is the physical address where the segment should be loaded. Notice the difference, right? So virtual address tells you which virtual address of this particular segment needs to be loaded, while physical address offset tells you which physical address this particular segment needs to be loaded, right? So typically, if we have like if we have an operating system like Linux, this physical address offset is not utilized, right? It is just ignored. Some embedded systems, for instance, that do not use an OS, do not use a memory management unit, would essentially make use of this physical address offset. But for all our needs, where there's an OS which is present and quite a sophisticated OS, then we ignore the physical address offset field, right? So then we have two more important fields which denote the size of this particular segment in the file and in the memory, right? So what does these two things mean, right? So we could have a segment which, when stored in the file, that is when stored in the hard disk, may be very small, or let's say 0 bytes, but when it is loaded into memory, then the size could be essentially expanded, right? So the size in the file for a particular segment may or may not be equal to the size in memory, right? So can you think of an example of when you could have a part of a program where in the file present in the hard disk, it's different from when it is stored in memory, right? So one example could be when you have global variables which are set to 0, right, or non-initialized variables. So they would be a different size in the file, that is when stored in the hard disk, and when loaded into memory, they would be of different size. Right? And finally, you have flags. So let's take an example of our hello program. So what we have done here is essentially now compiled hello.c like this. Okay, so this compiler option essentially creates the executable hello, and this is again the ELF. Has an ELF format, and we can use this readELF -l hello, which is created from the GCC compiler, to read the contents of the program header. Okay, now here is what is the program header for this hello ELF thing. So first thing you would notice that in the program header we have the entry point set to 0x4004B0, right? So this is the point, or this is the address where this hello program should start executing. Now this is a very critical address for us, because later on we would require the OS to set the program counter in a way so that the first instruction that gets executed when hello starts executing is at this location 4004B0. Okay. So then what we see is that in our program header, at least in our program header, there are 9 such program headers starting at an offset of 64, right? How do you see that it is essentially 64? This is obtained from the ELF header. So ELF header essentially says that if I go back here, so recollect this, right? So we have a pointer to program header, and the number of program headers in our example, the number of program headers is 9, and the pointer to the program header is essentially 64. That means 64 bytes into the offset of this hello elf is where we find this structure, right? And the program headers comprises of all of this thing. So since there are 9 such program headers, so there would be 9 rows, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. Now we have the type, which is essentially there are different types. So the loader type is important for us. There is a dynamic type, there's a GNU stack, relocatable file, there's a frame that is present. So this is essentially the type of that particular header. Now here is the offset within the file. So the load, for instance, is at an offset of 0. This second load is at an offset of E10 and so on. So the offset within this hello.file file is essentially present over here for each segment. Okay. So how is this useful? So this, for instance, I could look into my program header, look at a particular entry, and I could essentially identify where within my ELF file that particular segment is present, right? So this is essentially the offset within within the file. So then you have another entry called the virtual address. It essentially tells you where in the virtual address space of the process this particular segment should be loaded, right? So for instance, this second load is present at an offset E10 and should be loaded within the virtual address of 600 E10. So what does this mean, right? And how is it useful? So let's say that this particular segment comprises of code or data that is used by this by the program, right? So when the operating system wants to load this program, it would look into the program header. It would see that, hey, there is a section that needs to be loaded. This segment is present at an offset E10 within the hello.file. It also knows the and what it would do is it would copy this particular segment from an offset of E10 and load it into memory at this particular virtual address 600 E10, right? So we know now that there is a mapping between what is present on the in the ELF file and where that particular segment should be loaded in the virtual address space of the process. The third or the fourth entry is the physical address, right? Now for the executable view, this physical address does not make sense. So over here it's simply just a copy of the virtual address. So but we can just essentially ignore this part. The file size, there's a bit of a like alignment problem. Essentially tells you the size of the segment when it is stored on the hard disk, or in other words, the size of the segment in the hello file, right? So while mem size, on the other hand, tells you the size of the segment when it is loaded into memory. Now in many cases you would see that the size of the segment on the file is equal to the size of the segment when it is in memory, right? So for instance, here it is 7b4 on the file, present in the file, and when loaded into memory it takes the same amount of bytes, right? On the other hand, here the next segment, you see that it takes 238 bytes when it is present on the file, but when it is loaded in memory it takes 240 bytes, right? Now why is this happening? One possible reason in this case is that there is an alignment issue, and this segment was essentially aligned to some multiple, and this is creating this extra few bytes. So finally, we have the flags, right, which essentially tells you details about the segment. It tells you that this is a read write segment, but this is a read and execute segment. And in this particular way, for each segment that is present, you get to identify whether it's readable, writable, or executable, right? The last entry is the alignment, not very critical for us, but it essentially tells you the alignment of each segment. Okay, so thus we have essentially seen all the 9 program headers, and each program header corresponds to a particular segment and has details about the segment. Now, when the OS is essentially executing or creating a particular process using the exec system call, or executing a process using the exec system call, it would look into this program header and create the virtual address space accordingly, right? Also see at this particular point the mapping between segment and sections, right? So they are not two things. So recollect that uh, within the ELF header we have program headers, but you also have section headers, right? And it could be possible that you could have program headers pointing and section headers pointing to the same thing, right? So here, for instance, tells you the mapping between program headers and section headers. For example, things like dot interep, dot note, dot abi hyphen tag, and so on are the various sections, .gnu hash, dynamic sim, and so on. And all of these sections are essentially present in segment number 2. Similarly, .dynamic is a section, it's present in segment number 4. Right here we have .init array, .fini array, .jcr, .dynamic, .got, .got.plt, .data, .bss. So this is present in segment number 3, right, and so on. So what we see over here is that in the executable view, there would be a mapping between segments and corresponding sections.